In this video we're going to be looking at a Class C power amplifier, and it's very similar to figure 1244, page 422 of your textbook. And as you can see in this diagram, this the center of this entire circuit is a BJT amplifier, and I'm going to just go through some part selection options here for you in terms of just laying out the circuit. So what we have here is an AC source, a 5-volt RMS source, and under any of these options here at the top you have top menu you can select to get into your part selection window. So I'm just going to select one of these, and once the component window comes up, you have under your grouping sources. And while we're here, we'll just take a look at a couple of these. We have VCC, which is going to just be a typical DC power supply. By default, I think it's 5 volts and Multisim, but you can certainly change it. So we also have a ground. This is going to be earth ground, and this is what we'll use primarily for our circuits in this course. You also have a digital ground, but we won't investigate that. So lastly, we have our AC power source. So once we're satisfied with the component that we want, we drop that onto our component window, and then we have, just likewise, I'll just go ahead and put the other components. And what I like to do often is just go in and grab all the components that are needed and then position them and wire them after all the values and so forth have been changed or adjusted on each of the components. And then we go back to this VCC and we drop that there. Looks like I'd already changed the value, but let's go into this first source here, and we see that we have by default 120 volts. So what we're wanting is 5 volt RMS, so you can make the adjustment here, and you can adjust the frequency as well. Let's see what frequency I'm using on. Well, one other thing while we're here is the phase. We're going to have that as 0. By default, we'll just leave that at 0. But I wanted to check to see what frequency I had set here. Looks like 10.73 megahertz. Okay, so that's basically all there is for your AC source. And of course, the negative marking needs to be grounded with the earth ground. So I'll go get rid of that since we have one in the circuit already. And then VCC, again, you can just change the voltage. In this case it's 30, and that's really all there is to adjusting that voltage. So I'll get rid of this as well. Next we have capacitor. The initial voltage is going to be 0 on that, and it's a 220 picofarad capacitor. I'll just show you where to grab one of these capacitors, and then you can, once they're on the screen, you can actually right click and copy and then paste, and you don't have to go back to the library again to get the particular component, and you can just simply go in and make your adjustment, in this case your farad reading. So let me go and get rid of that one since it's a copy, and again back to our grouping. We have under basic, these are our basic types of components that we'll use. So capacitor, and under capacitor, well, notice you have a typical capacitor here that doesn't have any polarity. Then you have an electrolytic capacitor which does have a positive and negative reference. So we'll just use this typical capacitor that we could then select values from here, or if you don't find the one you want immediately, you can always just click OK, drop that on the Multisim window, and then go back in and then change, for instance, 220 microfarad. Okay, then we have, so we have capacitors at various areas in the circuit. So again, we can just make copies of the first one that we put in and then adjust values. The inductor, again, go to your basic components and we have an inductor value, and we'll just select one of these. Again, it doesn't matter which one you select because you can always go back in and change the value, in this case 1 microhenry. And notice that micro is U under our selection. Okay, so right now what I've got is an oscilloscope, and we've got a digital multimeter connected. And let's look at the multimeter first. Over on the far right, you see that you have some options. I'm hovering over this right now, and this is the Agilent multimeter. Again, you select it, dropped it into place. And then, since we're going to be measuring voltage, and here's a view of the multimeter. It's pretty realistic in terms of the layout of the buttons and controls and your inputs and outputs. So this first 3 represent these connections here. So we're going to be measuring voltage, so the top one goes into our circuit where we want to measure the voltage, and then we have our other common section. So let's close that out so you can see the wiring of that goes to ground. And so that's going to give us our voltage reading. And so what we're interested in is basically the base voltage, or prior to the base of this transistor. And then we have an oscilloscope, Tektronix oscilloscope, and we drop that on there, and then we can make our connections. Notice that we've got a G for ground. That should always be grounded. And then we've got 4 inputs that can be used to measure our signal. So right now what I've got, I was on channel 1. I'm going to go ahead and highlight that and delete that, just to show you that basically you just draw a wire connection from channel 1 to where we're wanting to measure our input voltage in this case. And since we're already grounded, we don't have to use the trigger or anything else. And the second one that I've got here is going to be on the actual output of the resistor here, the 1000 ohm resistor. And so let me get rid of this one here. So the purpose of this circuit is going to be a power amplifier, but it's going to create a signal at a resonant frequency, and you can determine that and calculate the resonant frequency of the output, and that comes from the properties of the capacitor and the inductor exchanging energy, and a timing scenario then gets created that results in an output frequency. So that's the purpose of the lab, and I'll just show you when I run the simulation. Certainly you can get the value here, so that's considered a measured value, and then what is being asked in the lab is to take screenshots of these at various times and locations in your circuit to verify that your circuit's in fact operating as intended. Okay, so under, let me turn this off. This is a very good representation too of the Tektronix oscilloscope. Turn that off. Right now what you're seeing on channel 1 is going to be the input, the 5 volt RMS. And again, it's always important to remember that if you're comparing values, peak to peak values with RMS values, that there's a conversion that you have to perform. So just keep that in mind when you're trying to compare, using the volts per division and determining the overall peak to peak, and then comparing that what you had in fact put on your input. So as long as you keep that in mind, you should be okay in terms of just knowing what your signal value typically is coming off something like this, like a front end here of a circuit, and then we'll do the same thing on the output. We'll want to know a lot of times what's on the output side. So that's what I have on channel 2, And it's a typical connection, again, to usually the last resistor in that chain. It gives you the connection point to the next stage, if you will, if you would use it in a more complicated circuit. So turn channel 2 back on. You see that there is a phase shift. You get that with oscillators. In other words, these are no longer, the output waveform is no longer in sync with the input. So two things are happening. You have amplification. And again, when I say amplification, sometimes that can be negative amplification or positive amplification. So again, you have a negative, you have a phase shift here, and then you have a frequency basically, and what that frequency is going to be from the beginning of one of the crossings, 0 crossings, to the next full wave. So when you're asked to confirm or verify frequency in this case, that's the frequency over time. And right now we're set at, this is the volts per division. We've got seconds per division. So I'm compressing that there, 10 nanoseconds. So make the adjustment until you can see a pretty good waveform, and then you can certainly use the tick marks and your seconds per division or volts per division to determine and confirm your calculations. Last thing we want to do is, once we have a screen up here that we have ready to take some screen captures, so under Tools, Capture Screen Area, then you have the ability to actually highlight or put a box around actually, let me move this up. Tell you what I'll do. Let's go back up here and do this again, since I had to. It's probably best to, in real life, you certainly would have your circuit powered off if you're making any adjustments, so we'll do the same here. It seemed like it was having some problem when I was running the simulation, and this is a software package that it has its limitations, and so we we'll often see some quirks, but there really are a lot of really useful features that represent the physical situation that you would encounter in Multisim. So here you could alt print screen if you wanted to paste it into Word. Like I said, you could also come over here, and once you've placed your capture screen area, you copy to clipboard, and you can paste that into Word. And you may do this a couple times and make some adjustments once you paste into Word so that you can see the figure, but that's essentially it. It's up to you. If you do an alt print screen, I think you'll just capture the entire screen area, which is okay, but it may then in fact make your data area, the most critical area, pretty small for display purposes. So that's about it for this video, and I'll see you in the next.